size so that you can see what's on there. Okay. Okay, can you see that a little bit better? So this is a simple command line app. It's a very simple linear regression model built with ML.NET. If you're new to machine learning, linear regression is one of several dozen machine learning algorithms that are used to fit a mathematical model to the data sets that you train the model with. Linear regression is where most people start learning machine learning because it assumes that there's a somewhat linear relationship between the points in a data set, and it fits a line, y equals mx plus b, which you may remember from high school geometry class, to that data set, so that in the future you can do predictive analytics by giving the model an x and letting it tell you what the y is. Simple linear regression uses two-dimensional data points with literally x's and y's. So what I've done here, let me first show you what the data set looks like. It's a simple CSV file with some poverty data for the 50 states in the United States. It shows, for example, the number of the percentage of residents in that state that live below the federally defined poverty line. And it also has some statistics regarding those states, like the teen birth rate. So our goal here is to analyze this data, to build an ML model around it, to see if there's a correlation between the poverty rate and the teen birth rate. And then once we fit the model to it, to be able to do predictions by saying, okay, if this is the poverty rate, what is the teen birth rate that we would expect in this state? So that's what the data set looks like. Let's go back to the code right here in Program CS. Whoops, didn't want to update it. There we are. So in the main method, we begin by creating an ML context object. That is the first and arguably most important class that you need to know about in ML.NET. Before you do anything with ML.NET, you create an ML context object. It's basically a state bank. It holds information about the model as you build it, as you train it, etc. It also exposes a bunch of properties and methods that let you do interesting things with that model. So in every example we look at in ML.NET, we will start by newing up an ML context object. The next thing we want to do is load the data from that CSV file that you saw a moment ago. Now, I'll say more about what I'm doing here in just a moment, but you'll see through the data operations catalog object exposed through the data property of the ML context, I call a method named load from text file. This is one way to load a data set into ML.NET. Now, notice that it is strongly typed. We're telling it that the data that we're loading from that CSV file has the shape of a class named input. Unlike most languages where you build machine learning models, C# is strongly typed. That's good because if you make errors, it's going to catch it at compile time rather than at runtime. So what I've done here is I've defined a class named input. The class name is not important. You can name it anything you want. But I'm telling it that from the data set that I'm loading, these are the columns that I want it to load. I want it to load from the first column, and the indexes are 0 based, the poverty rate data, and then from the fifth column, again 0 based, the data that I will call birth rate. So I'm loading XY coordinate pairs, poverty rate, and birth rate. Notice the attribute that says column name label on the birth rate property. Doesn't matter what I name that property. I don't have to name it the same as the name that it has in the CSV file. I can if I want. What's important is by using that column name label attribute, I'm telling ML.NET that when I do predictions with a trained model, it is the values in that column, birth rate column, that I want to do predictions on. You'll notice that I also define a class named output. Once again, we're using strong typing to specify what output we want from this model once it is trained, and we run it. That is, we use it to do predictions. And I tell it, well, I want to predict a birth rate. I'll give you a poverty rate. You tell me what the birth rate is. This column named score right here is very important. Without that, ML.NET will not do everything that it needs to do. This also tells ML.NET that when I run this model, it is this value that I want to see in the output. So with my data schema set up that way, I load those poverty rate and birth rate values from the CSV file. I then move the poverty rate column into a column named features. Now this is not documented very well, and it's not incredibly intuitive. But in a machine learning model, you can have any number of columns. There can be one or two of them, there can be tens of them, there can be hundreds. In some cases, there can be hundreds of thousands of them. That's pretty common in models that do genomics, for example. In ML.NET, you take all of the columns that you loaded from the data set that you want to use to train your model, and you aggregate them into a logical column named features. When you tell the model to train, it's going to look at that logical column named features, and whether there's one column in it, as there is in this case, or there are thousands of columns, it will use all of those columns in the training. I also, once I've done that, once I've defined the data that I'm going to train with, I tell it what learning algorithm I want it to use. Now, online gradient descent is one of dozens of classes in ML.NET representing machine learning algorithms. This is one way to do simple linear regression, to use their online gradient descent trainer. Once I've done that, I've defined the model. I've loaded the data. I've told it that I want it to look at the poverty rate column for the training. And I've told it what learning algorithm I want it to use when I tell it to train. Then I call fit on it to actually do the training. Now, this one trains quickly because there are just 50 rows in the data set. If there were 1,000,000 rows in the data set, it would take a lot longer to run. So fit is where I will spend my time waiting for the model to train. Once it's trained, I can use the model to make predictions. And the way I do that in ML.NET is I call a method on the model itself named createPredictionEngine. I tell it what the schema is for the input and the output. And now, if I want to make a prediction, I take a poverty rate that I want to use as the basis for the prediction, and I pass it to the prediction engine's predict method. If I could run this, and I can't because we're on GitHub, if I could run this, you would see that it would output a value for the birth rate that I would expect for that poverty rate. And if you actually charted this, say in Python, drew the line, the linear regression line that we fit to the data set, you can see that this value falls right along that line. So that's what the simplest possible ML model looks like in ML.NET. Just to recap, we begin by creating an ML context because everything we do in ML.NET is done through that context. We load the data. In this case, we loaded it from a CSV file. It can come from an infinite number of other places, which I'll say more about in just a moment. Then we tell it what columns, what features, if you will, we want it to train on by using that concatenate method to move all of those columns. In this case, there was just one, but there could be more into this logical column named features. Then we call fit to train the model. By the way, where did they get that method name? That's the method that you call in Scikit. If you're writing a model in Python, you call fit on it. Once I've trained the model, I call createPredictionEngine to create a predictor, and then I call predict on that predictor, giving it the input that I want to predict from, and it will give me the output. It's all strongly typed, as you can see. So again, if I've made an error somewhere, working with non-existent columns, or I have a typo in a column name or something like that, that'll be caught at compile time rather than runtime. Any questions about that? Yes, sir.
Just one minor. In the output column, you have an attribute column name.
Yes.
With the string score. Is that string fixed, or we can name it any way?
It is fixed. That's a good question. Let me go down here. When I define my output class, I'm telling the model here what output I want it to give me when I call predict on the prediction engine. And the question is, is there anything special about this here? Could I say column name output, for example? If I did that, it would generate an error. There is something magical in this name, and this is not documented very well. This particular model is a regression model as opposed to a classification model. And in ML.NET, when you build regression models and you define a class for the output by using column name score as an attribute, you're saying that this is where you want the output from the regression to be. This is the value that will hold the numeric output. And again, there's a little bit of magic here. It's always a little bit dicey when they use attribute names to make magic happen, but they are doing that right here. Okay? That's a simple model. Obviously, they'll get a lot richer and more complex. But those are the basics of building a very simple model with ML.NET. Now, let's go back over to PowerPoint. In that example, I called a method named load from text file to load data from a CSV file into memory so that I could use it to train a model. What actually happened there was that method call returned an object called the data view. The object implements an interface named iDataView. And there's not a lot of documentation on this either, but it's incredibly important what they've done here. With a lot of popular machine learning libraries like scikit, everything has to be done in memory. And if you try to train a very, very, very large model with scikit, it probably will not be able to do it. There's an upper threshold where it simply cannot handle it. When they designed ML.NET, one of their goals was to not only make it 10 times more performant than libraries like scikit, but to allow it to load and train on data sets of any size. The mechanism that they used to enable that was the data view. What's magic about the data view is that it's not just a .NET I enumerable. They actually looked at that early on and decided it wasn't sufficient. Data views are lazily loaded. So you can pump petabytes of data through this thing and use those petabytes of data to train an ML model, but the petabytes of data do not have to exist in memory at once. A couple of months ago, the ML.NET team at Microsoft published a white paper as a PDF where they published not only some performance tests showing ML.NET versus scikit and some other popular libraries, but also how much data they could handle. And they rather quickly, with Python and scikit, reached a point where scikit simply could not handle that much data. ML.NET, they threw 10 times as much data at it, it just blew it on out. So data views are the way data is represented when you load it and train machine learning models. And the beauty of the data view is that it is lazily evaluated so you can train models on massive data sets even with relatively small amounts of memory. Now, this creates a problem sometimes when you're debugging. You call a method like that load from text file and you want to see what's been loaded. If you put a debugger in your a breakpoint in your code right there, you'll find there's nothing in that data view because the data isn't actually pulled out until something pulls from the data view, until something reads from it. There's a method you can call named preview. If you've used pandas, the Python data analysis library, and you've used pandas data frames, there's a method called head that you've probably used that returns the first n rows of a data set. That's what preview does here. You use it when you're debugging. It goes ahead and pulls the first 100 rows from the data so you can see what's in there. It's not something you should use in production code because it does impact performance. But it's a neat little trick to know about when you're testing and debugging. Now, how do you load data? Well, once you have your ML context, it has a property named data, which is actually an object of type data operations catalog. And it has a bunch of different methods for loading data from various sources, like that load from text file method that you saw. It's great for loading data from CSV files, TSV files. It has a bunch of named parameters that you can use to tell it whether that TSV or CSV has a header, whether the delimiters are commas or tabs or something else. Basically, anything, any data set that comes from a TSV or a CSV or something like it, you can load that way. What may be more interesting is how do you pull data from other data sources? What if, for example, you have a big database sitting out there in Azure? You've got a bunch of data in it that you want to use to train a machine learning model. Obviously, that load from text file method is not going to help you load data from a database. So here's what you do, and this allows you to load data from any data source. In this example here, I'm just creating a simple array in C# called input, and I'm stuffing some objects into it. Then, instead of calling load from text file, I call load from enumerable. Now, that creates a data view that wraps everything in that enumerable, in this case, that array named input. Now, obviously, you don't have to create that array in memory. It could come from the results of a database query or something like that. But this is the generic non-text file way to get data into a data view in ML.NET. I'm going to go through this quickly to make sure we get through as much of this as possible. But one of the things you should know about ML.NET is this. Scikit is the world's most popular library for building ML models, and it's a Python-only library. Scikit does not have a lot of functionality for cleaning and preparing data. If you've worked in data science or machine learning before, you know that actually training a model is usually the easy part. The hard part is taking data sets, which are typically very rough, and preparing those so that they can be used to train a machine learning model. Python programmers rely on other libraries like the pandas library to do the cleaning. Typical cleaning operations will be removing duplicate rows, looking at rows or columns that have missing values and deciding what to do about those values. One strategy is to delete those rows or delete those columns. Another is to fill in missing values using some algorithm like filling them with the mean of all of the other values in the column. ML.NET has all of those capabilities built in. You don't have to bring in an external library. If you don't clean the data externally, you can bring it into ML.NET into a data view. And then there are a variety of methods that you can call to manipulate that data in various ways and make it sufficient for training a machine learning model. I've got some examples of that right here, but again, I won't spend a lot of time on that because we have more important things to get to. Here's something else you need to know about ML.NET. If you've ever worked with machine learning before, you know that you always like to have two data sets when you build a model, right? You need one set of data to train the model with. You need a second set of data to validate the model, to score it, to find out how accurate it is at doing predictions. If you train the model but you don't score it or validate it, then you really have no idea whether that model can make the predictions you want it to make. Now, in some cases, we go into a job with two perfectly good data sets, one for training, one for testing. More often, we have one data set, and we want to split it into two. One set for training, one for testing. In Scikit, there's a handy little method named train test split that does exactly that. Remember that a lot of the nomenclature that they used in ML.NET comes directly from Scikit because they knew that would be familiar to Python programmers all over the world. So guess what? ML.NET also has a method named train test split. It takes a data view into which you've loaded your data, and it lets you split it into a training set and a test set using a percentage that you specify. Some people like to use an 80-20 train test split. Some people prefer 50-50. You can specify that in your call to train test split. Now, let's talk about regression just a little bit. In machine learning, there are two fundamental types of predictive models that we can build. There are regression models and there are classification models. The purpose of a regression model is to predict numeric outputs. For example, you want to build a machine learning model around used cars. Given the type of car, its model, its make, its year, its condition, you want to predict what the price of that car should be. That's a classic regression model. We'll talk about classification models as well. Those are arguably more common. If we want to use machine learning to do spam filtering or sentiment analysis or OCR, those are classification models because we're not generating numeric outputs. Instead, we're saying here are the possible classes, spam or not spam. Here's an email, tell me which class that belongs to. ML.NET has a bunch of different classes, each implementing a different learning algorithm for doing regression models. The simplest is probably the OLS trainer. That is what we know of as simple linear regression. But there are much more sophisticated ones as well, like the light GBM model, which has been getting a lot of traction in the data science community lately because it tends to perform very well with very large data sets. There are others here as well. If you're familiar with decision trees and fast forest, there are learning algorithms already built in for doing this. So let's just go right past the description of some of the algorithms, and let's look at a little bit of code. Random forest is a very popular algorithm for building machine learning regression models. You can imagine if you have a data set with a bunch of points that fall roughly along a line, a linear regression model is probably going to work okay for that. But in the real world, data sets typically aren't shaped that nicely. Decision trees are one way that data scientists fit models to data that isn't shaped very well. They literally build a binary tree in memory saying, if this, then it's that value. If not, then it's this value here. The problem with decision trees is that they're highly prone to overfitting. If we allow the tree to grow deep enough and large enough, the model can memorize the data unless the data set is very, very large. So it will look like it performs very well when you train it, but when you apply it to real world data, it doesn't work very well at all. Fast forest is something called an ensemble method. It takes multiple decision trees, sometimes hundreds of them. Each of the decision trees in the random forest uses a subset of the data from the data set, and they actually train hundreds of decision trees and take the mean of all the results. Because they're training multiple trees over different parts of the data set, you virtually eliminate the need for overfitting. So it's an incredibly popular learning algorithm in machine learning. In this example, I'm using ML.NET to split a data set into a training set and a test set. I'm moving some feature columns named call1, call2, and call3 into that logical features column that ML.NET wants. And notice that I'm then telling it to use a fast forest trainer. Because I'm going through the regression catalog property, this is a fast forest trainer for a regression model rather than a classification model. There are also, when you use that fast forest trainer, there are a number of different options that you can leverage. This is called hyperparameter tuning. You can use the default parameters. You can often get slightly more accuracy by finding the right combination of parameters for that algorithm. This shows in ML.NET how you specify those parameter values. You create an options object, in this case, a fast forest regression trainer options object, and then you pass that to the fast forest method when you specify that you want to use fast forest for this model. Now, I think we've got 2 minutes before a break. How do you score a regression model once you've trained it? How in ML.NET do you test it with the test data set? It's kind of interesting what they've done here. They have an evaluate method that you access through the ML context object, and that evaluate method returns an object with a bunch of different properties, each representing a commonly used metric for regression models. R squared, for example, also known as the coefficient of determination, is probably the most popular way to gauge the accuracy of a regression model. Here, once I've trained the model with a couple lines of code, I can evaluate it using the portion of the data set that I set aside for testing. Then I can look at the R squared, or if I prefer other regression metrics, they're right there for me as well. One other thing you can do here is something called cross-validation. So here's the thing. It's very common to take a data set and to do, say, an 80-20 split. Use 80% of the data for training the model and the remaining 20% for testing it. Generally, that 20% that's pulled out for testing is randomly selected. But guess what? Depending on which 20% is selected, you can actually get different results when you evaluate the model. So a popular technique that data scientists use is something called cross-fold validation, or simply cross-validation. They'll divide the data set into, say, 5 folds, 5 20% splits. And then they'll actually train the model 5 different times, each time using 4 of the 5 folds and using the remaining fold to do the evaluation. Now, even though it's going to take longer to train the model because it's being trained 5 times, we get a more accurate indication of its accuracy, because when the model is cross-validated, it evaluates all 5 models that it's built, and it takes the average of those. So one mistake that we make sometimes is we will take that 20% of the data set we set aside for testing, we'll run an evaluation on it, we'll get the R squared, and we'll say, that's the answer. Nope. If you do a cross-fold validation, you'll probably get a different answer. Sometimes a little different, sometimes a lot different. As you can see here, a couple of lines of code in ML.NET are all that's required to do that. So let's take a 5-minute break. When we come back, I'm going to show you more models, more source code, and we'll go a little bit deeper into this.
And please log in to Eventrify applications and rate all presentations.